Implementation of microseismic monitoring for iron ore mines. The southern part of Ukrainian territory is situated on a seismic active zone. The most dangerous zones can be considered such regions as Transcarpathian, Ivano-Frankivska, Chernigivska, Odessa, and Crimea. The earthquakes in these areas have natural origin. Seismic activity is also increasing in the seismic territory of Ukraine, but earthquakes are mostly man-made. The Table 1 presents the list of earthquakes in the Kryvyi iron ore basin, Kryvyi, characterized by mining for 60 kilometers and a depth of more than 1,500 meters of underground works. Mining in this area causes irreversible changes in the stress-strain state of the massif, which intensifies dangerous natural and man-made processes, landslides, floods, earthquakes, mountain strikes, etc. It should be mentioned that the Kryvyi city itself is situated on the junction of some tectonic plates. Due to these factors, in Kryvyi iron ore structure, the earthquakes in amplitude higher than 5 may be caused. In addition to the general destruction of the basin, the seismicity of the zone is affected by industrial explosions and the presence of technological voids. Except the impact of industrial explosions on the man-made seismicity of the region also affects the mining works, which increases the seismicity of this zone. Man-made seismic phenomena, namely the collapse of the mountain massif, the exit of the funnels occurs when the limit values of rock tension is reached. The graph in the figure 1 shows the dependence of deformation on the rock's load of different geotechnical qualities. Approaching the limit value of the stress-strain state of the massif, segment AB in figure 1, is a condition of the danger zone. This dependence is the basis of microseismic control of the state of the massif. The task of control is to prevent the stress-strain state of the massif. Small cracks are registered with the help of microseismic monitoring. The number of cracks and their epicenter will indicate the stress of the massif. The increase in the number of cracks in time will indicate the second stage of plastic deformation, segment AB in figure 1, in which mining is a dangerous process. The registration of small cracks to predict powerful phenomena is the task of microseismic monitoring. Therefore, this method is called microseismic control. Due to microseismic activity, strong seismic phenomena can be predicted. In the technical literature, there is a well-known example of determining the stress-strain state of rock by the characteristic of the oscillation of the massif. In order to be able to predict local earthquakes, landslides, mining strikes, and safe mining operations at mining enterprises, it is necessary to introduce microseismic control. It will avoid material costs and increase the level of people's safety. It is important to control constantly or periodically the stress-strain state of the array for forecasting and prevention of dangerous natural and man-made processes. High sensitivity of measurement channels is required to control low-powered distractions. Along with the signals of destruction of random periodicity in the mountain's massif, there are constant fluctuations, microseismic. In most cases, the signals of microcracks are commensurate with the microseismics of the Earth. Due to the short distance to the expected phenomenon or to the monitoring area, it is possible to separate the impact of both microseismics and man-made noise. On figure 2 is demonstrated the example of Earth's microseism. The amplitude and frequency of the Earth's microseismic changes over time in a fairly significant range, 2-3 times. The example of microseismic on the surface of the mine Artem-1 in figure 3. It depends on several factors, for example, the seasons, the gravitational action of the Moon on the water, the distributed resonant qualities of the array, and others. But due to the random components or fluctuations in the level of the microseismic in time, the influence of factors is insufficiently studied. The low-power phenomenon differs from the Earth's microseismic in amplitude, frequency, duration, and shape, which can be seen in figure 4. To identify the phenomenon of the Earth, a microseismic is considered an obstacle. Any unloading of the massif is accompanied with creation of crack, which is characterized on the recordings by sharp increase in amplitude and a certain frequency of oscillation. Examples of a recording of the crack at the front of the mine are shown on figure 5. Due to the filtering properties of the array with the distance from phenomenon, the signal frequency decreases. Figure 6 shows the most remote signal in accordance with the frequencies of 92 Hz. In volume of geoinformational system of the mine, it is important to identify significant phenomena in terms of energy, territorial affiliation to the mine allotment, distance to the hypocenter, and the nature of the primary source, technical or natural. The experience of the use of microseismic monitoring for iron ore mines and size of working horizons of most mines has shown the feasibility of a monitoring radius within 400 meters. The horizons of existing mines, as a rule, usually have smaller widths. The location of the measuring probe is chosen by compromising between the requirement to approach to the phenomenon and the requirement of safety of measurement. To increase noise immunity, it is advisable to use both physical filtration methods and software selection of significant phenomena on the background of man-made noise. The processing is called the primary processing of measurement results. Conclusions. To identify the stress-strain state of the massif by the microseismic method, it is necessary to collect an array of data which includes the number of phenomena, the epicenter of the location of phenomena, and their power. High quality of primary data processing is achieved by using the identification of phenomena, namely Earth microseismics, cracks, collapses, rock strikes, explosions, mass explosions, man-made earthquakes. This is done by processing 14-16 indicators or factors of microseismic signals, the main of which are the frequency of oscillation of the array, the amplitude and duration of phenomena which are presented on the figures 4, 5, 6. Along with the well-known complex methods for determining the coordinates of the hypocenter of phenomena requires for spaced probes in the GIS of mines, it is advisable to use simplified methods for estimating the location of the epicenter using a single probe. According to amplitude of oscillations, we distinguish the power of the phenomenon and the distance. By the duration of the phenomenon, we can estimate the distance to the epicenter. Thank you for listening.